Hi everyone, Emil again. Today I'm going to go over doing an LSDA+U or DFT+U calculation, particularly with the U-Hubbard potential correction, or the U potential correction, U-Hubbard U correction, however you call it. So firstly, let's go over our in-car. It's a pretty standard setup. In this case, I plan on doing spin orbit coupling. So for that, you need to have I spin set to 2. I know, or I should expect to see a ferromagnetic ground state. So for my uranium atoms, there's 4 of them. I've set 4 uranium atoms to have spin up, right? This is equivalent to 1, 1, 1, 1, 4 ones, and 8 zeros. So that's germanium. I don't expect any magnetic ordering there. These are my convergence criterion, and this is the DFT+U. You're turning on the LDA+U tag. I'm using LDA+U type 1, which has a U and a U and a J correction here. In the previous video, I calculated for this U correction. I don't believe on VASP there's a way to calculate for this J correction. However, I'm getting this particular piece from literature. Lmax mix is set to 6, and that's pretty much all you need. So once you do your ground state calculation, you're going to do a self-consistent field calculation, such as the density of states. After that, we move to do a VASP non-collinear calculation. So rather than doing VASP_STD, we're doing VASP_NCL, non-collinear calculation. But that's later. Again, once we have that initial relaxation, we comment this out, and then we add the spin-over coupling. And in my particular case, I know that this is going to be along the A-axis. And this was experimentally found to be the easy A-axis and the most stable. POSCAR is going to be, the same. Your K points are going to be however you want it. There's nothing special, only the first editions of those tags in the in-car. So I'm just going to do that, and we'll check back when it's done. I already optimized my structure, and I also did a standard SCF collinear spin polarized calculation where I obtained my density of states. So I did have some problems optimizing. I just changed the optimization algorithm, or I should say I just changed the algorithm to all, and then that worked, converged perfectly. These are my density of states parameters. Once you have that done, you want to make a new directory. I like to make new ones just because I always like to refer to the original one rather than overwriting it. So from the previous directory where I did the original SCF collinear stuff, let's get the job file here as well. I pretty much copied everything the same, right? My in-car, my K points, my POSCAR, my POTCAR. Also, what you need in this is the wave car, okay? Because that's the whole reason of doing this, as well as the charge car. You don't want to change your densities, your charge densities. Do LL, make sure it's a real file, it's not empty, right? Your charge card's a massive file, couple of megabytes there, or hundreds thereof. So we have everything we need. Now, like I said, we did the in-car, okay? But we're gonna have to change some things. So you want to enable the following: LS orbit, and it'll turn on your non-collinear calculation automatically. Isometry S-axis, I think we're missing L max mix 6, and I charge is going to be set to 11. I believe that should be it. I will comment out the density of states. And we'll just grab the energies, make sure that it converges, so on and so forth. No, non-linear. Okay, yeah. So I'm just reading some notes. Make sure everything's all right here. Yes. So I'm not entirely sure if you can just head over straight to get the energy, right? Because that's all this is doing. It's going to get your energy with the spin orbit coupling. Or if you can just go straight to the SEF non-collinear here. But for the meantime, I'll just leave it just like this. And we also have to adjust our job file. It's not going to be VASP STD, right? We're going to do a non-collinear calculation here. So VASP STD goes to VASP NCL. And I'll just do spin over coupling. And that's pretty much, that should be it. So it's a very simple process. It's just a matter of navigating a bunch of things. So here we go. Right, okay, you have set 12 values for MagMom. Or for non-collinear calculations, magma has to be a list of 3 ions. And ions equals 12 in your calculation. Good. So, because we set S-axis to 1, the A orientation, in literature, I've seen for uranium germanide that is the easy A axis, as with the uranium telluride. So that's why I just set it to the A, right? That's the axis in which you're going to apply this spin over coupling or the magnetization and so on and so forth. If you don't know in the literature, if it doesn't say in the literature, then you leave it alone, or excuse me, then you have to probe the most stable orientation by doing 3 separate calculations, each one set to 1 or different values. It depends on, I believe, the space group, but that's something I have to look into. And then you find the lowest energy out of those. So now for your magnetic parameters, right? This is going to go from 8 to, let me think, 24. Because now you have an X, Y, and a Z component to your magnetic parameter there. Likewise, we're going to have 1, 0, 0, X, Y, Z, right? Ferromagnetic. They're all going to be 1, 0, 0. Uranium 1, uranium 2, uranium 3, 1, 0, 0, uranium 4, 1, 0, 0. Now, we should be all right to go. So that's it. Wave car is read successfully. Ooh, okay. That's symmetrizing. Ooh, this is an interesting one. I've never seen this before. All right, so I made a mistake previously. All you're supposed to copy over, right, is the POS car and the charged car. You're not supposed to use the wave car, which I mistakenly didn't realize, and we set I charge to 11. So now everything should work. I'll remove the charge. Cont das from the UGe2 I'll recopy charge car, and that's it. Ooh. Now run this in this. Ooh. Ah. Non-collinear, DFT+U, SOC. Now, we should be all good to go. It's taking this long, this is a good sign, because that's how it was previously. And go. Alright, so it looks like it's all done here. Let's check the total energy. We're at 91.54. And if we look at actually, if we check our previous one, we should be significantly lower energy, maybe an electron volt or two. Oh. Yeah, oh. 11 electron volts. It's interesting. $11 volts is actually quite substantial. This potent was set to 0.05. Okay, that's fine. It's not a crazy big deal. Okay. But besides that, all the other parameters are the same, so let's undo this and let's run the density of states calculation and see how that looks compared to our original one. Actually, let's set ISIM to 0 and see what happens there. And we'll check it again. So anyways, once you run the density of states calculation, you can see that we have the non-spin orbit coupled on the left compared to our spin orbit coupled on the right. So you can see that you don't get the spin contribution split when you have the spin orbit coupling, and that makes sense. You're just not going to be able to get it. There's a reason, a particular reason, because it's a non-collinear calculation that I don't know off the top of my head. But you can also do the band structure as well. These are how they look. I plotted these with Sumo band plot, so you guys could check the documentation there. It's called Sumo. I think it's fantastic because it really does. You work in the terminal, and you're able to generate the K points all in the terminal. Yeah, and it generates some really nice combo plots. This is a projected from the orbitals that I wanted to, from the F and D orbitals of uranium, as well as just the overall germanium contribution. Stacks them quite well. And that's pretty much it. If you guys have any questions, feel free to reach out in the comments below. Yeah, and that's it. That's how you do a DFT+U, particularly using the LSDA+U
for a uranium system. And again, if you want to see how to actually calculate the U values, I have that uploaded previously. Thanks again.